if I sketch out a circle, or sketch a circle in a graph, and attempt to sketch out the graph of the y-coordinate, and I hope the paper will stay put, but if I sketch out the graph of the y-coordinate with the point in the circle starting here, then my graph will go something like this. Okay, that wasn't very well done, but you get the idea, hopefully. Now, if I sketch the same graph, but start here on the y-axis, then I start at this point, and as I go around the circle, well, I'm not moving right, okay, come down to here, and down to here, and across to here, and so forth. Again, I'm not doing that very well. It's a little hard to coordinate that from this angle. A little hard to coordinate it, period. But if I start from the leftmost point, then I start by going downwards. So I go down and then back up. I'm having to watch two things at once, and I'm not able to do that very well. Maybe with practice, but I don't think it's going to happen today. In any case, if I start from the leftmost point, we can see that I'll start here. And if I start from the bottom, the lowest point on the circle, and move in the counterclockwise direction, then my graph's going to look like this. Okay? Now, a slightly better picture of that, drawn without trying to keep my eye on two things, is right here. You see that the graph that we got when we started at the rightmost point, that is like on the positive x-axis, is the green curve. The one starting on the leftmost point is the blue curve. Starting at 0 again, because the leftmost point is at x equals 0, but going in the negative direction, because if we start at the left side of the circle, we're going to go down before we go up. And then starting at the top of the circle, of course, we have this. Starting at the low point, the bottom of the circle, we have this. And these are the graphs that we get by varying the starting point on the circle. So by now we've seen that by varying the starting point in the circle, we can shift the graph left or right so that it starts really at any point between here and here, and it can start going either up or down. By changing the radius of the circle, of course, we can change the amplitude. We can make the thing come further or stay in closer to the x-axis. By adjusting the speed of the point on the curve, we can change the peak-to-peak distance, the wavelength or period that we're representing. We can bunch these up, put a lot of them in a small area, or we can spread them out. This might be hard to see. Let's see if I get just this sheet. I don't know if it's... You might be able to see just vaguely the graph moving back and forth. What I'm doing is I'm taking a graph here behind the paper and moving it back and forth. I can move it back and forth to match the various curves, but I don't think we're going to see that very well, so I'm not going to attempt to do that on the video clip. Here's an example where we go around a circle with an angular frequency of 3 radians per second out to a maximum y value of 5 or a minimum of -5. And we ask what is the period that corresponds to omega equals 3 radians per second. Okay? The period t is the time it takes to go once around the circle. Now, how long does it take to go around a circle at 3 radians per second? Well, the distance around the circle, the angular distance around the circle, is 2 pi radians, 6.28 approximately radians. It's about 6 radians if we use a ballpark figure, and if we're moving at 3 radians per second, we'll move 6 radians in 2 seconds, won't we? So the period is going to be somewhere close to 2 seconds. 3 radians per second, 3 radians gets us about halfway around a circle. We go the rest of the way in another second, or most of the rest of the way. So we make a period in just a little over 2 seconds, since we're going a little over 6 radians. If we analyze it very logically, t is a time for a cycle, which is a time for a revolution. Okay, to get that time, we take approximately the 6 radians and divide by the 3 radians per second and get 2 seconds. More precisely, we divide the exact distance, the 2 pi radians, by the 3 radians per second, getting 2 pi over 3 seconds. This illustrates what we do. We divide the 2 pi radians in a circle by the number of radians we go in a second, and that tells us how long it takes to get around. And that's the meaning of this equation right here. T equals 2 pi divided by omega. Here's a picture of going around a circle. We go 3 radians, another 3 radians. We take just a little longer. So we see why we divide the 2 pi radians in the circle by 3 to get the number of seconds it takes to go around.